Earth's atmosphere may appear empty when you look up, but in reality it is a complex, ever-shifting system. Filled with swirling gases and flowing thermal energy, it is alive with motion, constantly changing in ways we rarely notice. And some of its most spectacular displays only reveal themselves after nightfall. If you have ever watched a lightning storm tear across the sky, or a meteor shower streak through the darkness, or witnessed the soft, dancing glow of the aurora borealis in the north or the aurora australis in the south, then you already know just how extraordinary the sky can become. In recent years, with the help of highly sensitive cameras, scientists have begun capturing something even more elusive. Phenomena that were once only rumored, rarely seen, and almost never recorded. These brief flashes of light occur high above the storms we can see, in the upper layers of Earth's atmosphere. They are known as transient luminous events. What exactly are these strange flashes of light? Why have they remained hidden for so long? And what do they reveal about the invisible processes shaping our atmosphere now? Imagine a scene suspended between reality and something almost otherworldly. A structure that looks like a lightning strike, yet also like a living creature drifting through the sky. This is known as a red sprite. And the formation you are looking at is often called a jellyfish. A vast, glowing shape spreading silently across the darkness above a storm. It is enormous in scale, stretching across distances of up to 50 kilometers, and forming at altitudes between 70 and 80 kilometers above the surface of the Earth. Yet despite that size, a sprite exists for only a fleeting moment, lasting just 3 to 5 milliseconds, racing downward at speeds approaching 10% of the speed of light. For centuries, sprites were nothing more than whispers in scientific history. Reports of strange lights above storms date back to the 18th century. But it was not until the year 1925 that physicist C.T.R. Wilson proposed a possible explanation, suggesting that electrical breakdown could occur high in the upper atmosphere. Even then, it would take more than 60 years before technology finally confirmed that these elusive phenomena were real. So what exactly is a sprite? Unlike lightning, which burns at extreme temperatures, sprites are forms of cold plasma, more similar to the soft glow inside a fluorescent tube than to the violent flash of a lightning bolt. Inside that tube, an electrical current energizes gas, causing it to emit light. In a surprisingly similar way, sprites are triggered by powerful electrical discharges within storm systems. Inside a thundercloud, rising ice crystals become positively charged, while heavier particles, like soft hail, sink and carry a negative charge. This separation builds an electric field, and above the cloud, a layer of negative charge forms in the surrounding air. When a lightning strike occurs, it neutralizes part of the system, but that upper negative layer can remain unstable. It is this imbalance, this lingering charged region high above the storm, that can suddenly break down, releasing energy into the upper atmosphere and producing a sprite. And here is something even more intriguing. Sprites may not be rare at all. They are simply difficult to see. They occur high in the ionosphere, often hidden above thick storm clouds, far beyond the view of the human eye. To observe one, you need a clear line of sight above a thunderstorm, or a vantage point far above it, such as a high-altitude aircraft, or even orbiting instruments. Phasonsgram, on rare occasions, they have been captured from space, revealing just how vast and delicate these structures truly are. Sprites glow red, and that color is not random. At the low-pressure conditions where they form, nitrogen molecules become excited and emit a deep red light. This is very different from auroras, which often appear green because they occur at altitudes where oxygen is more abundant. And excited oxygen emits green light. But the story does not end there. Sometimes, a sprite triggers secondary structures that extend downward, like delicate tendrils reaching toward the storm below. These tendrils often glow blue. Even though they are also produced by nitrogen, the higher pressure at lower altitudes changes the way the light is emitted, shifting it toward blue and near ultraviolet wavelengths. The result can be breathtaking. A single massive sprite, glowing red across its crown, with faint blue tendrils stretching beneath it, like a luminous jellyfish suspended in the night sky. This phenomenon is known as a blue jet, discovered only relatively recently. Blue jets are a distinct type of transient luminous event, also triggered by powerful storm systems. In these moments, the positive charge building at the top of a thundercloud forms a conductive path upward, interacting with a negatively charged layer above the cloud and releasing a surge of energy that travels into the sky. As this energy rises, it excites nitrogen molecules in the surrounding air, producing a brilliant, cone-shaped jet of blue light. And that color is no coincidence. Earlier, we saw how atmospheric pressure influences the way excited gases emit light. Blue jets occur at lower altitudes than sprites, where the pressure is higher, shifting the emission toward blue wavelengths. There are also smaller, shorter-lived versions known as blue starters. Scientists believe these are essentially incomplete jets, discharges that begin to form but fail to fully extend upward. These smaller events typically reach only around 20 kilometers above the Earth before fading away. At the opposite extreme, there exists a far more powerful and towering phenomenon known as a gigantic jet. These reach much higher into the atmosphere, and because they span a wider range of altitudes, their color can shift dramatically, transitioning from blue at lower levels to red as they extend upward into thinner air. And then, at the very edge of what we can observe, there is something even more elusive. Among the rarest and least understood of these events are phenomena known as Elves. The name is actually an acronym, standing for emission of light and very low-frequency perturbations due to electromagnetic pulse sources. Despite the simplicity of the name, what they represent is anything but simple. Unlike sprites or jets, Elves do not form branching structures or upward plumes. Instead, they appear as vast, expanding rings of light, spreading outward high above thunderstorms. They occur even higher in the atmosphere, at altitudes of around 100 kilometers, and can reach diameters of up to 400 kilometers. And yet, despite their enormous scale, they are almost impossible to see. An elf lasts for only a single millisecond, a flash so brief that the human eye cannot perceive it directly. What we do know suggests they are triggered by intense electromagnetic pulses generated by lightning far below, sending ripples of energy through the upper atmosphere. Taken together, these phenomena offer a glimpse into a hidden world above the storms we see. A world of fleeting light, rapid energy exchanges, and delicate structures that exist for only fractions of a second before vanishing without a trace. And this is only the beginning, because this field of research is still young. There may be many more luminous phenomena waiting to be discovered, hidden in layers of the atmosphere we are only just beginning to explore. Now, imagine something very different. Picture the surface of the ocean on a dark and stormy day. Not calm and rolling, but chaotic, uneven, filled with deep troughs and jagged, rising crests. Now take that entire scene and turn it upside down, stretching it across the sky above you. It may sound surreal, But that image comes surprisingly close to describing a rare atmospheric formation known as asperitas clouds. These clouds are among the rarest ever recorded. Officially recognized only in the year 2017 by the World Meteorological Organization. The name asperitas translates to roughness or turbulence. And it is fitting, these clouds appear as chaotic, wave-like structures, unlike any other known formation. In fact, they are the first new cloud type to be formally added to the International Cloud Atlas in nearly 70 years. Because their discovery is so recent, much about them remains uncertain. Scientists are still trying to understand how they form, when they appear, and why they went unnoticed for so long. What makes them different, and what can they reveal about the complexity of Earth's atmosphere? The story of their discovery is just as fascinating. In the year 2006, an amateur photographer named Jane Wiggins, based in Cedar Rapids, Iowa, captured an image from her office window. She later described the scene as looking like the end of the world. She shared the image with a community of cloud observers, where it quickly drew intense attention. To many who saw it, this was not just an unusual sky, but something entirely unfamiliar, possibly evidence of a cloud formation that had never been formally classified before. Soon, more observers began contributing their own photographs, comparing conditions, noting patterns, and trying to understand when and where such a formation might appear again. As more data accumulated, the phenomenon caught the attention of professional meteorological institutions. Using dozens of independently captured images, researchers began assembling a case, carefully analyzing the structure and behavior of this unusual cloud type. After years of review and discussion, a decision was finally reached. For the first time since the mid-20th century, a completely new cloud classification was added to the official Cloud Atlas. Asperitas clouds became the first cloud type to be formally recognized through large-scale public observation. A rare moment where distributed human curiosity helped expand scientific knowledge. But why is that so unusual, and what actually defines a cloud as something new? To understand that, we need to step back for a moment. A cloud, at its most basic level, is a collection of tiny liquid droplets or solid particles suspended in the atmosphere. On other planets, clouds can be made of substances like methane, ammonia, or even sulfuric acid. But here on Earth, most clouds are composed of water, either in liquid form or as ice crystals. Clouds form when air becomes saturated and cools to the point where water vapor condenses into visible droplets. This process depends on temperature, pressure, and the presence of tiny particles that act as nuclei for condensation. There are several primary cloud types, including stratus, cumulus, stratocumulus, cumulonimbus, and cirrus. Each of these categories is further divided based on altitude and structure. In addition to these main groups, there are also supplementary features and accessory clouds that form under specific conditions, sometimes detaching from larger systems or developing unique shapes. All of these are catalogued within an international classification system that has been refined over more than a century. Updates to this system are extremely rare, which is why the addition of asperitas clouds stands out as such a significant moment. Asperitas clouds are most often associated with layered cloud systems at lower altitudes, though they have also been observed within other formations. Typically, these parent clouds have relatively smooth bases and more complex structures above, shaped by wind and temperature variations. But asperitas clouds reverse that expectation. Their most striking feature appears along the underside, where the cloud base becomes rough, chaotic, and deeply textured, resembling a turbulent ocean suspended in the sky. It is this unusual structure that sets them apart from more familiar wave-like formations. In 2017, researchers analyzed this phenomenon in detail, attempting to identify the mechanisms behind its formation. Their findings suggest that asperitas clouds may be linked to subtle oscillations within the atmosphere. Several processes could contribute to this effect. Air flowing over mountainous terrain can create wave patterns in the atmosphere. Differences in wind speed at different altitudes, known as wind shear, can introduce instability. Convection, the movement of heat and matter within air masses, can also play a role. Another important factor may be atmospheric gravity waves. Despite the name, these are not related to the ripples in spacetime predicted by relativity. Instead, gravity waves in the atmosphere occur when a disturbance pushes air out of equilibrium, and gravity works to restore balance. This creates a repeating motion, a kind of oscillation, where air moves up and down in wave-like patterns. You may have seen similar effects in the ocean, where waves rise and fall as energy moves through the water. In the atmosphere, a similar process can shape clouds into layered or rippling forms. But in the case of asperitas clouds, something disrupts that smooth pattern, creating a far more chaotic and dramatic structure. And that raises an even deeper question. What conditions are required to transform gentle atmospheric waves into something that looks like a storm frozen in time across the sky? Some familiar examples of gravity-driven motion include ocean waves, Ether's 5, and large-scale disturbances like tsunamis. In the atmosphere, similar processes can shape clouds into soft, repeating patterns. Formations you may have noticed before when looking up at the sky or out from an airplane window. From above, these patterns can appear even more striking, stretching across vast distances in delicate, layered waves. But asperitas clouds are different. They do not form smooth, rhythmic patterns. Instead, their undersides appear rough, chaotic, and deeply disturbed, more like a stormy sea than a gentle wave. This texture suggests something unusual is happening within the cloud structure itself. In many cloud systems, instability tends to form at the top, where differences in wind speed create what is known as Kelvin-Helmholtz instability, a process where layers of fluid slide past one another and begin to curl and break. But in asperitas clouds, this kind of instability appears where we would least expect it, at the base of the cloud. So what could be causing it? At this point, the answer is still uncertain. However, research suggests that disturbances from higher in the cloud may be propagating downward, especially if the cloud layer is thin enough to transmit those effects. It is also possible that the exact mechanism varies from one event to another. In one observed case, time-lapse imagery revealed gravity waves moving through a temperature inversion, a situation where a layer of warmer air traps cooler air beneath it. You may have seen this before, when clouds, or even smog, seem to sit beneath a distinct atmospheric layer. In this scenario, thunderstorms were present, but they were unable to draw in air from near the surface because of the inversion. Instead, they pulled air from above it. As gravity waves passed through this layered structure, they created regions of rising motion, forming strong updrafts that aligned with the peaks of the waves. This alignment amplified the motion, increasing the intensity of the wave pattern and producing the dramatic, uneven structure seen in the asperitas cloud. Regardless of the exact mechanism, what seems clear is that internal instability disrupts the smooth oscillations we typically associate with atmospheric waves, transforming them into something far more chaotic and visually striking. And when you think about it, the comparison to the ocean is more than just poetic. The same kinds of forces that create rough, choppy water during a storm, interacting flows, shifting pressures, and unstable boundaries may also be shaping the sky above us in similar ways. Different medium, same underlying physics. Nature does not repeat itself exactly, but it often follows familiar patterns. Even now, there is still so much we do not fully understand, and that realization leads us to another phenomenon, one that is not chaotic and dark, but delicate, luminous, and almost otherworldly. There are moments when the sky reveals something so subtle, so quietly extraordinary, that it feels as though you are witnessing something not meant to be seen. This is the case with noctilucent clouds. They form high above the Earth, in the mesosphere, under conditions so specific that they appear only rarely. And when they do, they seem to glow. Faint, silver-blue structures suspended in the darkness. What are these clouds made of? What causes them to shine long after the sun has disappeared below the horizon? And what might they reveal about changes happening within our atmosphere? Now, imagine a clear summer night. The sun has already slipped below the horizon, and somewhere in the northern sky, the star Capella shines steadily in the darkness. Then, almost without warning, a faint streak begins to appear low on the horizon. At first, it looks like a thin silver thread, or perhaps a soft swirl of icy blue light. Slowly, almost imperceptibly, it begins to brighten. The shapes sharpen, expand, and multiply until the sky itself seems to shimmer with delicate, glowing patterns, like a silent, luminous tapestry stretching across the night. These are noctilucent clouds, often called night-shining clouds, and they are among the most beautiful and mysterious phenomena in Earth's atmosphere. Despite their glow, they do not produce light of their own. Instead, they reflect sunlight from beyond the horizon, catching the last traces of solar radiation during what is known as astronomical twilight. When the sun sits between 6 and 16 degrees below the horizon and its light still grazes the upper layers of the atmosphere. Because these clouds form at extreme altitudes, typically between 76 and 85 kilometers above the surface, they remain illuminated long after the ground below has fallen into darkness. While they may exist during the day, it is only at night, when the lower atmosphere is in shadow, that they become visible to the human eye. To form a noctilucent cloud, 3 ingredients are required: water vapor, microscopic dust particles, and temperatures that are extraordinarily low. Unlike ordinary clouds, which form in the troposphere, the lowest layer of Earth's atmosphere, where most of the air mass and nearly all water vapor reside, noctilucent clouds form far higher, in the mesosphere, the third major atmospheric layer above the stratosphere. This region is difficult to study, positioned too high for conventional aircraft, and too low for most orbiting spacecraft due to atmospheric drag. These clouds form just below the upper boundary of the mesosphere, a region that is also the coldest part of Earth's atmosphere, where temperatures can drop below -100 degrees Celsius. For comparison, the coldest temperature ever recorded on the surface of Antarctica is about -89.6 degrees Celsius. In such extreme conditions, tiny ice crystals begin to form, each less than 100 nanometers in size. These crystals gather around dust particles, creating the faint, shimmering structures we observe from the ground. Interestingly, the mesosphere must reach temperatures of around -120 degrees Celsius for these crystals to form efficiently. And yet, despite requiring such intense cold, Noctilucent clouds appear during summer. This apparent contradiction is explained by an unusual property of the upper atmosphere. During summer, warm air rising from the lower layers expands and moves upward. As it rises into the thinner air of the mesosphere, it cools dramatically through a process known as adiabatic cooling, making this region colder in summer than in winter. Because of these precise conditions, noctilucent clouds are rare and seasonal. They typically appear only for a window of about 60 to 80 days each year, often peaking roughly 20 days after the summer solstice. They are most commonly observed at latitudes between about 50 and 70 degrees north or south. Beyond these regions, especially closer to the poles, the sky remains too bright during summer nights, making it difficult to observe these faint structures, even though they may still be present high above. So if you happen to live in places like northern Norway or Alaska, you might actually need to travel south to get the best view of these night-shining clouds. But while we have learned a great deal about them, there is still much we do not fully understand. To begin with, the mesosphere is an incredibly dry region. In fact, it is estimated to be about 1 million times drier than the air above the Sahara Desert. Not exactly the kind of environment where you would expect clouds to form. So where does the moisture come from? One leading idea is that air rising from the lower atmosphere carries water vapor upward into the mesosphere. But an even more puzzling question remains. Where does the dust come from? One possibility is space itself. Every day, Earth is bombarded by countless tiny particles, fragments of meteoroids and cosmic debris. Over time, these particles may accumulate in the upper atmosphere, providing the surfaces needed for ice crystals to form. But is that enough to explain such widespread cloud formations? Or could there be other, less obvious sources? There is an intriguing historical clue. Noctilucent clouds were first documented in the late 19th century. Not long after the massive eruption of Krakatoa in 1883, that eruption sent vast amounts of ash and debris high into the atmosphere. It suggests that large-scale events may play a role, injecting material into regions where it would not normally reach. We also know that human activity can occasionally trigger similar effects. Rocket launches, for example, can release particles and water vapor directly into the upper atmosphere. In some cases, this has led to the temporary formation of artificial noctilucent clouds. But without such direct causes, the origin of these clouds remains difficult to pin down. To better understand them, scientists have turned to space-based observation. A dedicated satellite was launched to study this region in detail, focusing on the formation and behavior of ice particles in the mesosphere. Equipped with instruments designed to detect dust, measure atmospheric conditions, and capture detailed images of these clouds, it has provided valuable insight into a region that is otherwise extremely difficult to observe. By combining data from satellites with observations from aircraft and ground-based instruments, researchers are beginning to build more accurate models of how these clouds form and evolve. And this research is not just about understanding a beautiful phenomenon. The mesosphere is highly sensitive to changes happening elsewhere in the atmosphere. Because of its low density and unique conditions, even small variations in temperature or composition can have noticeable effects. In that sense, it acts like an early warning system, revealing subtle shifts that may be linked to broader changes in Earth's climate. Over time, observations have suggested that noctilucent clouds are becoming more frequent. Some scientists believe this may be connected to long-term climate trends, where warming in the lower atmosphere leads to cooling in the upper layers, creating more favorable conditions for their formation. Understanding this region also has practical importance. It plays a critical role in the behavior of spacecraft during re-entry. And studying its properties can even help us better understand the atmospheres of other planets, including Mars. The The more we learn about the mesosphere, the more we begin to see how interconnected Earth's systems truly are. But as we continue to observe the sky above us, there is another realization slowly taking shape. The atmosphere is not just a place of natural beauty and hidden physics. It is also a place of observation. And whether we notice it or not, something up there is always watching. The Earth is surrounded by eyes. Not distant, mysterious watchers hidden beyond the stars, but machines we built ourselves. Quiet, precise, endlessly patient. Hundreds of satellites drifting above you right now. Each one observing, recording, learning. Some carry mirrors as powerful as the Hubble Space Telescope, but instead of looking outward into the universe, they are turned back toward Earth, toward cities, oceans, and toward you. Others don't rely on visible light at all. They see through clouds, through darkness. Whether it's day or night makes no difference. Radar pulses, infrared signatures, subtle changes in heat and motion, these systems reconstruct the surface of our world with astonishing clarity. And they are getting better. In an age where data is the most valuable resource, governments track threats, companies optimize behavior, and algorithms learn patterns we didn't even know we were leaving behind. Every movement, every signal, every digital trace becomes part of a larger picture. A picture that is constantly updating. So the question is no longer whether we are being observed. It is how much and why. Because the same technology that helps monitor climate change, predict natural disasters, and guide rescue missions also makes privacy harder to define. And even harder to protect. At what point does awareness become surveillance? At what point does safety begin to cost something more? For most of human history, looking up at the sky meant wondering what might be out there. Now, it might mean wondering what is looking back. And somewhere, silently crossing the darkness above, something captures another image, another data point, another moment. The question is, if you knew exactly how clearly you were being seen right now, would you look up and smile? In 1957, everything changed. The Sputnik 1 was launched by the Soviet Union, officially as a scientific experiment, a way to test communication signals through the atmosphere. But beneath that explanation was something far more powerful. It was a statement. A signal to the world that the space race had begun. And the world did not take long to respond. 50 years later, by 2007, there were already hundreds of active satellites orbiting Earth. Then, in just a decade, that number nearly doubled. By 2022, it had surged into the thousands, and it continues to rise. Companies like SpaceX are planning constellations of tens of thousands of satellites, forming vast networks that wrap around the planet. Within the next decade, we may be living beneath a sky filled not with hundreds, but hundreds of thousands of machines. Of course, not all of them are watching. Many are built for communication, navigation, and science. But even so, there are still thousands dedicated to observing Earth. Thousands of silent observers, each one collecting fragments of information. And over time, they have become extraordinarily precise. There is a concept known as spatial resolution. It describes how much detail a satellite can capture, how much of the ground is represented by a single pixel. Early systems, like Landsat, had a resolution of about 80 meters per pixel. That means a single pixel could cover an entire football field. These images were useful for tracking weather patterns, coastlines, and large-scale environmental changes, but not much else. There was distance. There was anonymity. But that distance has been shrinking. Modern satellites now capture imagery at resolutions as fine as 1 meter, sometimes even better. Systems like Carbonite, too, can record full-color video from orbit, tracking the movement of vehicles, the shifting of waves across the ocean, the slow transformation of cities in real time. And this is only what is publicly available. Other systems push even further. Some reach 50 centimeters, 25 centimeters, even down to 16 centimeters under certain conditions. At that level, the world begins to change. Patterns become individuals. Movement becomes behavior. And observation becomes something far more intimate. Of course, these capabilities come with undeniable benefits. Traffic can be monitored. Natural disasters can be tracked. Urban growth can be understood in ways that were once impossible. But there is another side to this evolution. Because as clarity increases, so does concern. The earliest reconnaissance satellites, like those developed under the Corona program, relied on physical film. Images had to be captured, stored, then physically returned to Earth in capsules. It was slow, limited, almost fragile. Today, everything is digital, continuous, instant, and far more enduring. Governments rarely disclose the full capabilities of their surveillance systems. But what we do know is enough to raise questions. Not just about what can be seen, but about how much is being seen. Right now. Because somewhere above you, at this very moment, a satellite passes silently overhead, capturing light, capturing motion, capturing detail. And the difference between being part of the landscape and being part of the data is becoming harder to define. So the question is no longer whether the sky is full of eyes. The question is, how clearly do they see you? The United States has laws in place that limit how detailed satellite images can be, at least for commercial use. These restrictions are meant to prevent resolutions from becoming too precise. But companies are increasingly pushing back, arguing that global competition does not follow the same rules, and that staying within these limits may mean falling behind. It is important to understand that this is not really about what is possible. The laws of physics do impose challenges. To achieve extremely high resolution, a satellite would need to fly closer to Earth, where atmospheric drag becomes a problem. Or it would require a mirror so large that launching it into space becomes extremely difficult. These are real constraints, but they are not absolute barriers. Because of that, it would be misleading to assume that spy satellites cannot go beyond current public limits. There have long been rumors suggesting resolutions of 10 centimeters or even finer. Some have speculated about resolutions approaching 1 centimeter, though those claims remain unverified. In 2019, an unexpected moment brought some of these capabilities into the spotlight. During a failed rocket launch in Iran, an image of the damaged site was shared publicly by Donald Trump. The intention was to show that there had been no external interference. But what caught the attention of analysts around the world was not the message. It was the image itself. The level of detail was striking. After careful analysis, experts concluded that the resolution must have been around 10 centimeters. Possibly even better. This was far beyond what is typically available to the public. To understand what that means, imagine looking down at a city street with that level of clarity. At this scale, you are no longer just seeing vehicles. You can distinguish fine details like tree branches, subtle textures, even the colors of clothing. The scene becomes vivid, almost immediate. And then there is the next question. If that is what 10 centimeters looks like, what would 1 centimeter reveal? The technology behind these systems already exists. Some of it has been partially observed. Advanced reconnaissance satellites, such as those in the Keyhole series, are believed to have optical systems comparable in size to the Hubble Space Telescope. In fact, it is widely known that similar mirror technology has been shared between scientific and defense applications. This suggests that there may be multiple space-based observatories with capabilities far beyond what is publicly acknowledged. If even a fraction of these systems were dedicated purely to science, our understanding of the universe might look very different today. But instead, many of them remain focused on Earth. And we are no longer living in a world where darkness or cloud cover guarantees privacy. Modern systems can operate across multiple wavelengths, using radar and infrared to see through conditions that once provided natural concealment. Which means that the idea of being unseen is becoming harder to hold on to. The sky above us has not just become more crowded, it has become more aware. Synthetic aperture radar imaging works very differently from traditional cameras. Instead of collecting visible light, these satellites send down radar pulses and measure how long it takes for those signals to return. By repeating this process over large areas and combining the data with extreme precision, they can reconstruct detailed images of the ground below. This technique allows satellites to simulate having a much larger mirror than they physically carry. And because they generate their own signal, they do not depend on sunlight. They can see through clouds. They can operate at night. In many ways, they remove the last natural barriers that once limited observation from space. At this point, it is natural to feel a sense of unease. The idea that at any moment you step outside, something far above could be tracking movement, following patterns, observing behavior, not reading the details of your life directly, but mapping enough of it to understand where you go and how you move through the world. And while that level of observation may not yet capture the smallest personal details, the direction of progress is clear. But this is only one side of the story. Because the same technology that raises these concerns also provides extraordinary benefits. Satellite data allows us to monitor weather systems, track climate change, measure rising sea levels, and observe carbon dioxide concentrations in the atmosphere. It helps scientists study ice sheets, surface temperatures, crop health, irrigation patterns, and water quality across entire continents. With radar systems capable of penetrating clouds, satellites can detect heat signatures from wildfires, helping emergency teams respond more quickly and effectively. They allow us to follow the development of hurricanes, map dust storms, and better understand the forces shaping our planet. In one remarkable case, data from a satellite originally designed to study cyclones was used to track locust swarms across eastern Africa. By identifying regions rich in moisture where locusts breed and feed, researchers were able to help reduce the scale of outbreaks, protecting crops and supporting food security for millions of people. So the technology itself is not inherently good or bad. It depends on how it is used. There are clear advantages for science, safety, and global understanding, but there are also incentives that feel less comfortable. Businesses can use large-scale data to track consumer behavior and population movement. Governments can monitor activity for security purposes. In many cases, these actions are justified. They prevent harm, improve infrastructure, and support decision-making. But they also raise a difficult question. Once a technology exists, how do you control how far it goes? Because the line between protection and intrusion is not always clearly defined. And history has shown that tools created for one purpose can evolve into something else entirely. Perhaps this is simply part of progress. As long as there are benefits to greater precision and deeper insight, development will continue. It is difficult to slow that momentum, and even harder to reverse it. But understanding it matters. Because the more clearly we see what is possible, the more thoughtfully we can decide what we are willing to accept. And maybe that is where the real balance lies. Not in stopping the technology, but in deciding, collectively, how it should be used. You can decide for yourself how this makes you feel. Whether it is something unsettling, or simply part of the world we now live in. Whether it calls for stricter regulation, or whether it is a necessary trade-off for the convenience and security of modern life. Wherever you stand, perhaps it is worth remembering one simple thing. When you step outside, when you move through your day, there is always a chance that something, somewhere above, is watching. So maybe, just smile. Now imagine something very different. Imagine the force of 100 nuclear explosions happening at the same time. That was roughly the energy released by the eruption of Hunga Tonga Hunga Hahapai, one of the most powerful atmospheric events ever recorded by modern instruments. And the strongest eruption since the 1883 Krakatoa eruption. The shockwave from this event did not simply fade away. It traveled around the entire planet multiple times. A pressure ripple circling the Earth again and again. It was detected across continents. And in some places, it was even heard. From New Zealand to Alaska, the sound carried across vast distances. A reminder of just how much energy had been released in a single moment. The eruption triggered tsunamis, devastated nearby islands, and sent ash and dust high into the atmosphere, where it spread across the globe. Events like this are rare, but they reveal something fundamental. The Earth is not still. It is not quiet. It is a dynamic system, capable of sudden and overwhelming change. Now bring that scale closer. Imagine you are inside a building, at home or at work. Everything feels normal, until suddenly, the ground begins to move. At first, it is subtle, then stronger. Shelves rattle. Objects fall. The walls begin to sway. You realize what is happening. An earthquake. And then a thought appears. Almost instantly, there is another floor above you. A ceiling held up by structures you cannot see. As the shaking intensifies, a single question begins to repeat in your mind. Will it hold? During the 2024 Noto Peninsula earthquake, this was not imagination. It was reality. Families gathered together at the start of a new year suddenly found themselves in the middle of violent ground motion. Buildings shook. Infrastructure failed. And in just moments, lives were changed. Hundreds were lost. Many more were injured. And yet, in a country like Japan, earthquakes are not rare events. They are part of daily life. Over decades, Japan has experienced one of the highest frequencies of major seismic activity in the world. But even within that context, some events stand out. Some behave in ways we do not fully expect. Some challenge what we think we understand about the earth beneath our feet. Because beneath the surface, far below where we live and build and move, forces are constantly shifting. Plates grinding, stress accumulating, energy waiting, and sometimes, without warning, it is released. Not as a single event, but as something more complex. A pattern, a sequence, a swarm. And what we are beginning to discover is that some earthquakes are not just isolated ruptures. They may be part of something larger. Something that does not end when the shaking stops. Something that may even have the power to subtly change the way our planet itself moves. So the question is no longer just when the next earthquake will come. The question is what exactly is happening beneath us right now, and how much of it do we truly understand? Japan sits on the western edge of the Ring of Fire, one of the most tectonically active regions on Earth. Vast plates of rock and soil are constantly shifting over millions of years, sometimes pulling apart and sometimes colliding. What makes Japan even more complex is that it lies at the intersection of several smaller plates, all interacting at the same time in a slow but relentless geological struggle. The Pacific Plate pushes westward and slides beneath the Philippine Sea Plate and the Okhotsk Plate. At the same time, the Amurian Plate presses against the Okhotsk Plate, while the Philippine Sea Plate also subducts beneath the Amurian Plate and the smaller Okinawa Plate. It is a layered and intricate system, a kind of continuous collision that not only formed the islands of Japan, but also built up enormous tanav beneath the surface over time. When that built-up energy overcomes the friction holding these plates in place, the result is sudden movement. That movement is what we experience as an earthquake. But the earthquake that struck the Noto Peninsula in January 2024 was different. It caught many people off guard, because this region is not located along one of Japan's major fault lines, and scientists are still trying to understand why such activity is happening there at all. If you look at earthquake data over the past 25 years, most seismic activity clusters along the eastern side of Japan, where the Pacific Plate dives beneath the Okhotsk Plate. Even earthquakes that occur further west are often deeper underground, reflecting how far the subducting plate has already traveled beneath the surface. But this event did not follow that pattern. Instead of striking in the east, it occurred in the west, in Noto. There are other unusual signs as well. Over the past 3 years, the region has experienced tens of thousands of small tremors in what is known as an earthquake swarm. Since 2020, the ground beneath Noto has been quietly but persistently shaking. Normally, this kind of activity is not considered especially dangerous. In many cases, numerous small earthquakes release energy gradually, reducing the likelihood of a much larger event. But Noto did not behave as expected. The swarm lasted longer than typical models would predict, and instead of fading away, it culminated in a powerful earthquake in early 2024. Scientists are still uncertain why this happened, and that uncertainty is part of what makes this event so significant. The impact was severe. The earthquake reached a magnitude of 7.5 and struck at around 10:40 in the evening, local time, on New Year's Day, when many people were at home with their families. It was not a single shock, but a sequence of events, with numerous foreshocks and aftershocks rippling through the region. There were more than 1,200 aftershocks recorded, spread across an area over 150 kilometers wide. At least 7 of these reached magnitude 5 or higher. Around 40,000 homes lost power almost immediately. Roads fractured, buildings collapsed, and emergency systems were activated across the region. Authorities quickly issued a tsunami warning along the western coast of Japan. In some areas, the first waves arrived within just 1 minute. Waves as high as 5 meters were expected, adding another layer of danger to an already devastating situation. And as the ground continued to shift and settle, one thing became clear. This was not just another earthquake. It was a reminder that even in a country deeply familiar with seismic activity, the Earth can still behave in ways we do not fully understand. Although much of the recorded footage showed waves only 1 to 2 meters high, the force was still powerful enough to sweep away buildings along the coast. In total, there were hundreds of deaths, more than 1,000 injuries across multiple prefectures, and economic losses exceeding $18 billion. Entire communities were disrupted in a matter of moments as the ground shifted beneath them. But one of the most unusual aspects of the Noto region is what had already been happening beneath the surface long before the main earthquake. Since 2020, scientists had detected a gradual uplift of the peninsula. The land had risen by about 3 centimeters, suggesting that something was building up underground. It could have been water. It could have been magma. But the exact cause remains uncertain. When the earthquake finally struck, that slow movement turned into something dramatic. In some areas, the land rose by as much as 4 meters. The coastline itself was reshaped. The boundary between land and sea shifted outward by around 250 meters, leaving certain ports suddenly stranded, no longer connected to the ocean. When changes of this scale occur, they do not remain local. The redistribution of mass across the Earth's surface can influence the way the planet rotates. Just like a spinning dancer changes speed by adjusting the position of their arms, the Earth responds to shifts in how its mass is arranged. During the 2011 Tohoku earthquake, a magnitude 9 event, the length of a day was shortened by about 1.8 microseconds. It is an incredibly small change, almost impossible to perceive. But it is measurable, and it reveals just how interconnected the systems of our planet truly are. An earthquake in one region can subtly affect the entire world. No matter where you are, your life is, in some infinitesimal way, touched by these events. Because of this, scientists across the globe are working continuously to better understand earthquakes. Not only their causes, but also their consequences. For countries like Japan, where seismic activity is a constant reality, understanding is not enough. Preparation is essential. To improve resilience, Japan's National Research Institute for Earth Science and Disaster Resilience has developed one of the largest earthquake simulation systems in the world. This facility can test structures up to 10 stories tall. Using real seismic data to recreate the forces of major earthquakes. Through these simulations, engineers have been able to refine building designs, strengthening beams, joints, and structural supports. These innovations can determine whether a building remains standing or collapses under stress. Interestingly, advances in space technology have also contributed to this field. Knowledge developed through aerospace engineering has influenced how structures are designed to absorb and distribute energy. A striking example of this is the Tokyo Skytree, standing at 634 meters. Built in one of the most earthquake-prone regions in the world, it was designed with a deep understanding of how structures respond to motion. Its stability is not just a matter of strength, but of flexibility, balance, and precise engineering. And in that way, even in the face of immense natural forces, there is something quietly reassuring. We may not be able to stop the Earth from moving, but we are learning, slowly, how to move with it. Engineers achieved this by designing a central concrete column about 360 meters tall, supported on massive rubber bearings and connected to the outer structure through fluid dampeners originally developed during the Apollo program. When an earthquake strikes, the central column and the outer frame of the building move at slightly different rhythms. These motions counteract each other, reducing the overall sway and stress placed on the structure. In some cases, this system can reduce the force transmitted through the building by up to 50%. Even with such advances, earthquakes still come at a heavy cost. Lives are lost, homes are destroyed, and entire communities are forced to rebuild from the ground up. In the Noto Peninsula, recovery has been a gradual and difficult process. Damaged roads initially slowed emergency response and repair efforts, making it harder to reach affected areas. Over time, power has been restored to most of the roughly 40,000 homes impacted. But months later, hundreds were still without electricity. Many thousands remained without water, and large numbers of people continue to live in evacuation shelters. Events like these are powerful reminders of the forces that exist beneath us at all times. The ground we stand on may feel stable, but deep below, immense energy is constantly building and shifting. When it is released, the results can reshape entire regions in moments. And yet, there is another side to this story. In places like Japan, where earthquakes are a part of life, people respond not only with resilience, but with innovation. Engineers, scientists, and communities work together to better understand these events, to predict them more accurately, and to reduce their impact through smarter design and preparation. Every advancement, every insight, contributes to a broader understanding that benefits not just one country, but the entire world. By studying what happens beneath our feet, we learn how to live more safely on the surface. Because the world we inhabit is both dangerous and beautiful. It is constantly changing, shaped by forces far beyond our control. But within that change, there is also possibility, the possibility to adapt, to learn, and to endure, and perhaps that is the quiet truth beneath it all. We may not be able to stop the earth from moving, but we are learning, step by step, how to stand strong when it does.